Welcome back to the second module of the course. In this video, we'll be understanding about Hadoop cluster. Basically, Hadoop cluster is divided into two parts. The first one is the HDFS layer and MapReduce layer. We'll discuss about HDFS layer first. Let us continue. So in HDFS layer, first of all, in a cluster, you'll be having a lot of nodes, right? In all the nodes, among all the nodes, you need to identify one of the node as a master node and others as slave nodes. These are all slaves. Slave nodes can be a commodity hardware, that means a cheap hardware, but make sure that the hardware for master will be good. Why we'll discuss later. So you have identified, let's assume in your cluster you have 3 nodes and you have identified this as master and these two as slaves. So on master node we have to start a daemon called as name node. What is a daemon? Daemon is nothing but a background process, nothing but a Java program which will be running in the background. So on master machine we need to start a Java process called as name node which will be running on some port, and on the slave machines we need to run data node daemons. Okay, the names are confusing actually. Name node, it's actually saying the name is node. Actually this is not a node, it does not represent a machine, it is just a process, Java process. Similarly, data node does not represent a machine, it is just a daemon Java process. So on master we should have name node running, and on slave we should have data node running. What is the purpose of these nodes? Let us try to understand. First, let us discuss about HDFS layer, then we will discuss about MapReduce layer. We will forget about MapReduce layer as of now. Assume that you have a file of say size 100 MB and let the file name is a.txt. Now you want to write this file into HDFS. How do you write it? So what we do is we submit the file to some program called as Hadoop client. So we'll discuss about how to start a Hadoop client and how to send the data. Assume that this is a Hadoop client machine, a machine which is having Hadoop client program. So what we do is, if I want to store 100 MB file on the cluster, I need to first give that 100 MB file to this Hadoop client. Now what this Hadoop client will do is, Hadoop client splits this 100 MB file into 2 blocks, or we call the blocks are also as input splits. The Hadoop client will split the input into input splits, but right now we will not go into the terminology, we will go into terminology next. Let us try to understand the concepts at a high level now. Hadoop client will break 100 MB file into 2 blocks. Block 1, let's say block 2 of size is 64 MB and 36 MB. Now Hadoop client will ask the name node, hey, I have a file, I have a block of 64 MB, where shall I store it? Name node will respond to the Hadoop client and asks that block 1 should be stored in one of the data node. So assume that the replication factor is 1. The name node, let's say it says store the block 1 in data node 2. So here the block 1 has to be stored, right? The Hadoop client, what it will do is it will again make a connection to data node 2 and ask the data node to store block 1. Okay, let me explain you with a clear diagram. I'll open my OneNote. I'll draw a diagram clearly. Assume that you have a cluster of 6 nodes: node 1, node 2, node 3, 4, 5 and 6, and let's assume that this is the master and rest all are slaves: slave 1, slave 2, slave 3, slave 4 and slave 5. Okay, now through Hadoop client, this is HDFS client, I'll say HDFS client. Whenever I want to store 100 MB file, I'll pass a 100 MB file with name say a.txt to this HDFS client. On master machine, we understood that there should be a daemon called as name node running. Name node, I'll say NN. Hadoop client, what it will do first, it will break this 100 MB file into 2 blocks. Block 1 of size 64 MB and block 2 of size 36 MB. Now, the Hadoop client connects to name node process and asks the name node, hey, where can I store this block 1? Assume that now the replication factor is 3. Okay, name node will respond saying, save this block 1 under slave 3. Actually, in slave 3, assume that there are data node daemons running. So I'll say D1 on slave 1, D2 is a data node 2, D3, D4, D5. Now the name node, when the client asks where to store block 1, the name node might respond saying, store that block 1 under D3, D1 and D5. Now Hadoop client, what it will do is it will connect to first node, what is it, D3, and it will write block 1. So block 1 will be present here, and also block 1 will be written to where, data node 1 and data node 5. Block 1 will be present here, block 1 will be present here. Then Hadoop client will ask, where shall I write block 2? So block 1 is present in data node 1 and 3 and 5. Block 2 will be, again the name node response saying, store it in under data node 2, data node 1, data node 6 or data node 3. Okay, so block 2 is present on here, data node 2 here and here. The metadata about where each blocks are present for this file is stored inside main memory RAM of name node. So name node maintains the metadata of the blocks, where each block is stored under which data node. Okay, so now I have a simple question. Who is actually writing data to data nodes? Is it name node or the client? Client only. Initially the client connects to name node and asks, where shall I store these blocks? Name node will just respond saying, store this block 1 under D3, D1 and D5. Then Hadoop client or HDFS client only is responsible for establishing a socket connection to data node daemon and then sending the blocks. We will see in detail about exactly how writes happen. There is some more things to discuss, but at a high level understand this is happening. Name node is storing the metadata of the blocks and the files, everything under its main memory, and data nodes are responsible for storing the actual blocks. Okay, and data nodes will be communicating with name nodes at some regular interval, and they will be sending something called as heartbeats. Name node should somehow understand which data nodes are alive, is it? At some regular intervals, the data nodes will send heartbeats to name node, so that name node can understand which all data nodes are still alive. Okay. Suppose if one of the data node is not sending heartbeat for a specified amount of time, the name node will assume that this data node is dead, data node is not reachable, name node will identify what all blocks are present in this data node 4. It will try to replicate those blocks under other nodes and will update the metadata accordingly. So if one of the data node is down, name node will identify that the data node is down because it is not receiving heartbeats from it, and it will try to replicate the blocks again to maintain the replication factor of 3. Okay, any doubts? Just think for a while, analyze whatever I have said. Okay, so you got some basics of HDFS. You understood that there are two daemons, name node and data node running. How does name node and data node interact with each other? This might be your question again. They internally use remote procedure calls for talking to each other. Data node should send heartbeats to name node, right? So how does it send heartbeats? How does data node communicate with name node? Using some remote procedure calls. It is not HTTP. Remember, this might be some questions in certifications. It is not. They are not interacting with each other through HTTP ports. They are using RPC. Okay. So coming to name node, the metadata of the files is stored in memory of name node, which is running on master machine. So it will not store the data in hard drive. There is no demand paging in name node. Everything is stored in main memory. What do I mean by metadata? Metadata means list of all files. So how many files are present in the cluster? The list of all files, and for each file is comprised of how many blocks? The list of all blocks, and list of data nodes for each block. Same block 1 might be present in data node 1, data node 5 and data node 7. The list of data nodes for each block is also maintained inside the metadata, and also the file attributes, like what is the access time of the file, what is the replication factor of a file. All such information we call it as metadata. All this metadata is stored inside main memory of name node. Okay, and also it maintains the record. It also records the file creation times, file deletion timestamp, etc. This information also is present in metadata of name node. Now you might have some questions again. What if name node crashes? Yes, name node is a single point of failure in Hadoop 1.x version. If you are working with 1.x, name node is a single point of failure. But in Hadoop 2.x, there came a concept called as name node high availability. We can configure name node high availability so that if one name node is down, another name node will take the place of the primary. Don't worry about what is HA. We have a detailed discussion on how to configure HA in Hadoop 2.x going on further. Now coming to the discussion, we already understood that name node holds the metadata. Assume that on your cluster there are two files, foo.txt and bar.txt. Name node will maintain for foo.txt what are all the blocks? Block 1, block 2, block 3. For bar.txt, what are all the blocks? Block 4 and block 5. Name node also maintains this metadata, the blocks for each file, and also each block is stored in whichever data nodes. See, block 1 is here, block 1 is here, block 1 is here. The replication factor by default is 3, and each block size will be 64 MB. In Hadoop 1.x, the block size by default is 64 MB. In Hadoop 2.x version, the block size, the default block size is 128 MB in size. These are the default values. Of course, we can configure them. I will show you that configurations. Okay. So name node holds only metadata, whereas data node hold the actual data blocks. How does the client write files to HDFS? As I told you earlier, whenever client wants to write a file, the client will split the file into blocks. Now client will ask, hey, where shall I write my block A? The name node will respond with the locations where to write, and then the client will write the data to corresponding nodes. This is same as what we discussed earlier. Going to low level, let us see the flow. So the HDFS client, whenever it wants to create a file, at the API level, what the HDFS client will do, it will ask the DFS, the distributed file system, on the client machine. This is API actually. It will call create method on distributed file system, which will ask the name node to create a file. That means metadata is created in the memory for a file. And name node will respond, store the blocks in these locations. Then the HDFS client, what it will do, it will open a data stream and will write to the corresponding data node. Assume that there are 3 data nodes, data node 1, data node 2 and data node 3. Assume that the file which you are trying to write contains only one block B1. Okay. HDFS client has asked the DFS to create a file which contains one block. Name node will respond, hey, store this block 1 under D1, D2, D3. Now the client will use data output stream, FS data output stream, and write the packets to data node 1 only. Block 1 has to be written to where? Data node 1, data node 2 and data node 3. The client will not write to all the data nodes. Client will write only to the first data node. Okay. It will send the data to first data node. This data node 1 will take the responsibility to write the data to data node 2. Then data node 2 will write to data node 3. At a low level, this is what is happening. And once the data is written, the acknowledgement will be sent back. This is how file write happens in HDFS at a high level again. We'll go to even low level going on next. So whenever you are writing a file to HDFS, the blocks of a particular file are stored over the cluster. If you have seen the data nodes in your data center, all the machines will be kept in some racks, is it? Rack 1, rack 2, rack 3 and n number of racks. So in one rack there can be n number of machines where the data nodes might be running. So whenever you are writing, say, a file of size 1 GB, 1 GB means how many blocks? 1 GB by 64 MB, okay, that number of blocks. So the client writes will span over the whole cluster. More the number of blocks, the more the file is wider spread. The client writes span the whole cluster, and it will maintain a replication factor of 3. Okay. Can you tell me why replication factor is required? Why the blocks needs to be replicated? This is a common question which I get. That means if you want to store 1 terabyte of data in your cluster, 1 terabyte, you end up writing 3 terabytes of data. Is it okay? Yes, this is required in any distributed system, because if you are storing only one replica of the block, you earlier understood what if the machine goes down? You cannot retrieve the file data, is it? So to avoid failovers, taking failover into consideration, assuming that the data nodes may fail, we need to replicate, otherwise the data will be lost actually. Okay. So don't worry, anyway the data nodes will be running on commodity hardware. That means cheap hardware only. The data nodes, the machines where the data nodes are running need not be costly hardware, they can be commodity hardware. Because even though one of the node fails, it's okay. The name node will take care of replicating the data. So that is the reason why data nodes can run on commodity hardware, that means cheap hardware. Even if one of the node goes down, that's not a big issue, it can be taken care, the replication of data can be taken care. Okay, next. So as I told you, name node determines the replica placement. Name node will decide where the replicas should be placed, and whenever replicas are decided, it will make sure that replica placements are rack aware. Okay, what do I mean by rack aware? Coming back, see, assume that this is one rack. The racks are connected to each other over switches in the network. Assume that my file has only one block. Block 1 is returned to data nodes belonging to same rack B1. Here only B1, again B1. What if some network problem is there in the switch? The whole switch is down. Okay, that means you will not be able to reach the whole rack. That means your file is lost. So the name node will make sure that whole replicas, all the replicas of a single block will not be written into same rack. What it will do is, it will make sure that the first replica of block 1 will be stored in a rack, any one of the rack, and it will select another rack for storing block 2 and block 3. So name node is rack aware, we say. Okay. So first replica on a local rack, second replica on local rack but different machine, third replica on a different rack. So it is rack aware. So if you see the diagram, let's assume that my file contains block 1 and block 2. Block 1 is placed in rack 1. Block 1 is again placed in same rack 1. Another replica is kept in another rack. So if this whole rack is down also, my data is not lost. The block is present in another rack. So replication, the name node is rack aware. The name node runs a script called as rack awareness script, which will tell which nodes are present in which racks, and based on that the name node will take a decision. So don't worry about what is this rack awareness script, we will see in detail next. Now some of the few questions which you might have in your mind right now is how to configure the RPC port of data node for data transfer. So earlier we understood that data node is a daemon running in the background. So data node might be running on some port, is it? How do you configure that port on which the data node starts? You need to configure a property called as dfs.datanode.address. If you don't configure anything, the data node will by default run on 50010. Okay. So this is 50010 is the port at which the data has to be sent. But data node also runs another HTTP server as well. So this is the property which you need to set for telling on which port the data node should run. By default, if you don't do anything, this is the port at which the HTTP server runs. Okay. Don't worry about where to configure these properties. We will see where to configure these properties in detail. But I want you to remember from examination point of view, certification point of view, that the default port for data node for data transfer is 50010, and HTTP server on data node is running at 50075. You may ask a question, hey, why is a HTTP server required on data node? We will see. If you want to browse the files and the blocks present in each data node, you may require HTTP server. We will see the use cases of HTTP server. Right now, understand that there is a HTTP server also running at 50075. Okay, next. Now, till now you understood HDFS part of Hadoop. Now, coming to the other part, I'll come back. As we discussed, Hadoop cluster is divided into two parts. One is HDFS layer, which we discussed till now, and other is MapReduce layer. So, in again MapReduce layer, there are two daemons which will be running. On the master machine, we need to start one more daemon called as job tracker, and on the slave machines, another daemon called as task tracker has to be started. Okay, and you might have one question: is it required that name node and job tracker should be running on same machine, same master machine? And you may also ask me, is it always mandatory that there should be only one master machine? No. You could identify two machines as masters. One master machine where only name node can run, and one machine where another master 2, I'll say, where job tracker can run. So job tracker and name node need not always run on same master machine. We can identify two master machines, and we can make sure that name node will be running on one master machine and job tracker will be running on another master machine. How to make sure where the job tracker runs, how to determine where the name node runs and job tracker runs, we'll see the configuration next. But for now, assume that name node and job tracker are the daemons which will be running on master machines. There can be more than one master machine as well. Task trackers are the daemons which should be running on slave machines wherever data nodes are running. Okay. Now, once you understood about job tracker and task tracker, let us try to understand their purposes. Okay. Let me submit a MapReduce job. I'll come back. Okay. So, you know that whenever you are storing files will be stored on data node, and metadata is maintained inside name node. Now, coming to this, assume that you have let me just draw the diagram instead of showing you here. I'll just draw the diagram. Okay, assume that again you have a cluster of say 8 nodes. I have identified this as master 1, this is master 2, two master machines, and these are all the slave machines: slave 1, slave 2, slave 3, slave 4, slave 5, slave 6. Assume that I stored say access log, and the size of access log is say 100 MB for simplicity. Okay. Now assume that 100 MB is split into block 1 and block 2. Block 1 is stored on S1, S4 and S6, and let's assume that block 2 is stored on S2, S3 and S5. Now on master 1, assume that name node is running, and on master 2 assume that job tracker is running. Now on the slave machines, there will be task trackers running on slave machines. So task tracker 1, task tracker 2, Hmm? Task tracker 3, task tracker 4, 5 and 6. Okay. Now what I want to do is I want to submit a job to the cluster. I have written some MapReduce job. Let's assume that I have written some jar, say my job dot jar. We'll see how to write MapReduce jobs later. What I should do is through a client program, through HDFS client or through Hadoop client, what we should do is we should submit the job jar to job tracker. Whenever a job is submitted to job tracker, the client will always submit the jobs to job tracker only. So what happens whenever client submits job to job tracker? Job tracker will identify where are these blocks B1 and B2 present. Block B1 is present in where? S1, S4 and S6, and block 2 is present where? In S2, S3 and S5, right? So job tracker will contact the name node and identify where are these blocks for the file present. You have submitted a jar which has to analyze the access log. So whenever job tracker got the job to analyze this access log, it will identify what are the block locations for this file. The name node will respond saying that block 1 is present in all these nodes and block 2 is present in all these nodes. Job tracker will pick up the first nodes S1 and S2. Then what the job tracker will do is it will send the job jar file to task tracker daemon running on this S1 and task tracker daemon running on this S2. So the job is transferred to task tracker, and task tracker will make sure that the tasks are executed on the data which is local here, right? So again, in MapReduce there are two types of tasks. Don't worry about what I am speaking on right now. If you don't understand, you'll get it slowly. In MapReduce job there are two types of things which we need to do. Map phase, there are two phases, map phase and reduce phase. We'll be writing a class called as mapper and we'll be writing a class called as reducer. So once a MapReduce job is submitted, first the task trackers will execute map tasks. The task tracker will start a map task and execute the mapper. Okay, see this diagram now once more. If you see this diagram, you can understand easily. So once the job is submitted to job tracker will send the job jar to the task tracker. Task tracker, what it will do, it will start one map task which will call the mapper. The data is executed. So the task trackers will execute map tasks. Then after all the map tasks have been executed, then the output of map tasks will be passed to something called as reducer tasks, right? Who is starting the reducer tasks? Again, one of the task tracker will run the reducer task, and the output of reducer task is again returned to the distributed file system. This is the flow at a high level whenever you submit a MapReduce job. So the job tracker will submit the jobs to task trackers. Task trackers will take the responsibility of executing the jobs, and task trackers will be sending the task status to job tracker. Job progress will be sent to job tracker, and the client will be retrieving the job progress from the job tracker. Okay, so at a high level this is a MapReduce flow. We will understand the details of MapReduce programming, how to write a MapReduce program and how to execute it. All the inner level details we will see. In this video I am just trying to give a high level idea. Okay, now Again, some few questions you might have. Let me just answer your questions using the diagram. Okay, now see this diagram. The job tracker has identified that block 1 and block 2 are present in S1 and S2, and the job is submitted to task trackers, task tracker 1 and task tracker 2. Task tracker 1 and task tracker 2 are responsible for executing the MapReduce jobs on these machines. One question which may come to your mind is, what if while the job is getting executed on this machine, what if the machine is down, machine is crashed? Will my job fail? No. If this machine crashes, the job tracker will identify that it is not getting heartbeats from the task tracker. As I told, task tracker will be sending some heartbeats to job tracker, which heartbeats contain the information about the job progress. So if the job tracker is not getting heartbeats from a particular task tracker, it will assume that the task tracker is down, and it will try to find where is block 2 present. Here it was actually working on block 2, right? In what other node is block 2 present? Yes, here. The job tracker will again submit the same job to task tracker 5, which will again start running the task on this local machine. So partial failure of a job will not result in the total failure. If one of the block processing fails, it will not result in total failure of the job. The job tracker will try to identify another block, another task tracker, and it will run the jobs, it will run the tasks on another task node. This is called as speculative execution. Job tracker will identify the failed tasks and it will reschedule them to be executed in another task tracker. Okay. So partial failures of jobs are taken care by Hadoop. We need not worry about partial failures. Okay. So that's what I want you to understand in MapReduce at a high level right now. Now, you understood the core components of Hadoop are HDFS and MapReduce. You understood at a high level how MapReduce works and how HDFS works. And you understood about some daemons like name node and data node, job tracker and task tracker. I have a small question now. Just try to answer yourself. Name node and data node belongs to what? What part of Hadoop? These are the daemons belonging to HDFS. Job tracker and task tracker are the daemons belonging to MapReduce engine. So data node and name node are responsible for storing data and the metadata. Job tracker and task tracker are responsible for executing the tasks or the jobs. Okay, so that's what we understood till now. Then let us try to understand why Hadoop. Why should I use Hadoop? What are all the features of Hadoop? So before understanding why Hadoop, let us try to understand what are the typical requirements for a distributed approach. One of the typical requirement of distributed approach is system should support partial failure. Is my Hadoop supporting partial failure? Yes, right? Let me explain you whatever I have explained. Assume that these are the slave nodes in which task tracker is running. Task trackers are running here. And whenever a job is submitted, assume that the job is given, the map tasks are running inside T1 and T2 here in these two machines. If this machine goes down, the job tracker will identify that this task tracker is down and it will reschedule the same task to be executed on another task tracker. So failure, partial failure of one of the nodes in the cluster is supported. Failure of a component will not result in the failure of entire system. Of course, it may result in graceful degradation of application performance. That means when the same task has to be executed again, there is some time wastage, is it? Some time has spent while executing the task on this machine, but it is a wastage. So whenever there is a partial failure of one of the nodes, it will result in degradation of the performance, but it will not result in the complete failure on entire system. So Hadoop supports partial failures. Okay, next. If the component of a system fails, its workload should be assumed by still functioning units of the system. Yes, failure should not result in loss of any data. If one of the data node is down, is my cluster down? No. The other data nodes also might be having same replica of the data. The other nodes will take the workload. So if one of the component fails, its workload will be assumed by existing nodes. Failure will not result in loss of any data. So if one of the data node is down, anyway there are replicas, the data is not lost, data is recoverable. Hadoop supports this feature as well. And if a component of a system recovers, it will be able to join the cluster again. Let's assume a simple scenario. I will try to elaborate on this. Let's assume that you have a cluster of say 6 nodes. I'll clarify all the doubts. You are having one file, say a.txt in block 1 and block 2. Assume block 1 is here, block 1 is here, block 1 is here, block 2 is here, here and here. Now assume that the node, this last node is down. Name node will be getting heartbeats from all the data nodes, is it? So the data node on this machine will not be able to send the heartbeat. So name node will identify this node is down, and the name node will identify what all are the blocks present in this one, B2. It will try to replicate B2 on another machine. So let's say it will replicate B2 on this machine. Okay. After some time, assume that this data node comes up. What will happen? This is again containing block 2. So how many replicas of block 2 are present? 1, 2, 3, 4. 4 are present. But I want replication factor to be 4. After this block, after this node comes up, it will be able to join the cluster, and whenever this node joins a cluster, the data node joins a cluster, it will send a heartbeat to the name node and say, hey, I'm again still having block 2. Now the name node identifies that block 2 is present in 4 nodes, and it will issue a rebalancing command to the cluster. So the blocks will be rebalanced. That means during rebalancing, the name node may ask this data node to delete this block 2, because anyway block 2 is replicated in another node. So that is already taken care by HDFS. We need not worry. So whenever a component which failed earlier recovers, it will be able to rejoin the system, and Hadoop supports this component recovery. And also we understood component failures during execution of job should not affect the outcome of the job. As I told you, if your job is executing in task tracker 1 and task tracker 2, if task tracker 2 fails, job tracker will identify the failure and it will reschedule the same job and on another task tracker. So this is called as speculative execution. As I said, component failures during execution of job will not fail the whole job. Partial failures are still supported. So Hadoop supports this consistency feature as well. And assume that the load on the system is heavy. That means there are a lot of jobs executing on your cluster. What you should be able to do is, if you add few more nodes, the load will be distributed evenly again on all the nodes, right? Adding load should result in graceful declination in performance of individual jobs. It should not result in the failure of the system, right? So let's assume that my cluster supports 100 jobs per hour, but what if the number of jobs submitted is 150 jobs per hour? It should just result in graceful declination of the performance, but the programs should not fail. In case if you want to support 150 jobs per hour, you may need to add some more nodes so that the performance will increase. So Hadoop supports scalability. You will be able to scale horizontally. That means if the load on your cluster is more, you will be able to add new nodes to the cluster, which will again balance the load. Okay, so any distributed system requires all these points. Hadoop anyway supports all these things. That's why we can use Hadoop for distributed processing. Okay, so now we understood why should we use Hadoop, because Hadoop supports what? Partial failure. It supports data recoverability, component recovery, and consistency and scalability. So we can use Hadoop for distributed processing. Okay, so till now we understood what is Hadoop, HDFS, MapReduce at a high level, and why Hadoop. Let us now discuss about basic Hadoop concepts. First, coming to the history of Hadoop. Hadoop is based on actually work done by Google in late 1990s. Google has published a paper on Google File System, GFS, and in 2003 this GFS has been published, and MapReduce is based on the Google File System, which is published in 2004. The core concept of Hadoop is what? Distribute the data while storing it among multiple nodes. Individual nodes can work on data local to these nodes. So the core concept of Hadoop is, while storing the data, let's say you are storing a data of say 100 MB, while storing the data itself, distribute the data among multiple nodes, and whenever you are submitting the jobs, let the jobs be transferred to the individual nodes, and the jobs will be working on local data on both the nodes. So distribute the data as it is initially stored on the system, so that individual nodes can work on data local to those nodes. Jobs will execute on local data. That is the core concept of Hadoop. So if jobs are transferred to the place where data is residing, there is no data transfer over the network for processing. So that will increase the performance. This is the core concept of Hadoop. So in Hadoop, data is spread among the machines in advance. That means the data is stored in HDFS. Computation happens where data is stored. And also you understood that in HDFS, data is replicated multiple times for increased availability and reliability. And is there a requirement that nodes should talk to each other, the data nodes and all? No. Nodes need not talk to each other. The data nodes need not be aware of other data nodes. Everything is taken care by Hadoop. Developers can just focus on writing their application logic, and developers need not worry about how the jobs will be distributed, how the data is stored. You need not worry about all. You can just concentrate on the business logic. You need not worry what happens if one of the node is down. What happens if one of the task tracker fails? You need not worry. Hadoop will take care of it. So developers can focus on application logic only. And Hadoop supports fault tolerance, as I said. As I told you, if one of the node fails, the master will detect that failure and reassign the work to a different node on the system. As I told you, the job tracker will detect the failure of task trackers and will reassign the work to a different node, right? Restarting a task does not require communication with other nodes. What do I mean? Assume that you have submitted a job and the job is getting executed on task tracker 1, task tracker 2, task tracker 3, task tracker 4. Assume that when the job is getting executed, your job is executed parallelly on 4 nodes. If this third node fails, what the job tracker will do? It will try to reassign the same job to another node on which another task tracker will be running. So if this fails, do you think the other task trackers should be intimated about this failure? No. Restarting a task does not require communication with nodes working on other portions of data. This is not required. Next. If the failed node restarts, what will happen? It automatically gets added to the system and it will be assigned with new tasks. This we have already understood. And also, if a node appears to be running slowly, let's assume that you have submitted a job and the job is executing on 4 nodes, and this node is slow, a bit slow compared to all other nodes. The job tracker will be able to identify a slow node and it can execute the same task on another node automatically. This is called as speculative execution. Now whichever task completes first, that will be taken into consideration and other tasks will be killed automatically. So Hadoop supports such a kind of speculative execution as well. Okay. So that's about Hadoop basic introduction. In our next video, we'll see how to install Hadoop on 3 modes: local mode, pseudo distributed mode and distributed mode, and I'll show you practically whatever I have explained. So in this video you have understood theoretically about HDFS cluster and also the MapReduce engine, and what happens when file is stored on the machine, and what happens when a job is submitted to MapReduce engine, how job tracker daemon and task tracker daemon communicate with each other, and we also understood how job tracker supports partial failures. We also understood about speculative execution. See you in next video to understand about installation of Hadoop.